Okay, so let's continue our journey through transformers. We already discussed the use of transformer in the seek-to-seek model, where we replaced the RNN encoder with a self-attention mechanism, which we call transformer. Here we want to see if such representation learning can be used in a maybe more familiar domain of vision and image classification, something that we almost solved using our CNNs. And we want to see if transformers can be as useful as the proven CNN, or maybe they can beat CNNs. Then we will talk about an architecture that is known as vision transformer within this comparison. There are some challenges within that we will talk about with some solutions. Okay, so like I said, we replace RNN with transformers. And the main reason that we did that, it was because RNNs had this sequential processing that led to slow training, and thus they could not be scaled. They also had this vanishing gradients that prevents us from going for a very long sentence or text during the encoding and decoding. We added attention, across attention more specifically, that allows the decoder to attend to all of these hidden states in the encoder, but still we are doing the encoding with the recurrent neural networks, which is still a bottleneck. Adopting a transformer architecture, basically dropping the RNN entirely, led to a fully parallel architecture, which is much faster and can be scaled while using all of our GPUs. And also having a global context. Really, the distance between words or token didn't matter for self-attention. Every pair of tokens could attend to each other. We discussed the design of transformers where the residual connections help the gradient flow. And then we discussed this machine translation problem solved by transformer and how it became the state of the art. So now the question is, if transformers beat RNNs for sequence, can they also beat CNNs for images? Well, for images, like I said, we had a good run with CNNs. So let's see if the transformers are up for this challenge. So back in 2020, CNNs were still the dominant paradigm for vision. We had very efficient designs using ResNet and EfficientNet. We had a lot of excellent benchmarks like ImageNet and other data sets that allowed the community to do a lot of development and advancement and introducing different techniques to make CNNs really work well. The question is, if we had more data, can CNNs still improve? Is there maybe we can recast the question like this? Does CNNs with their philosophy, their inductive bias, have the flexibility to continue improvement with more data? So then the experiment was, okay, so machine translation solved by transformers. Can we do the same for images? The idea is transformers are very flexible, so we don't need to really do a lot of modification. We just need to find a way to represent the images as input or tokenize them in a way that we can feed it to the transformer. And that's it. The rest will be just waiting for the result and the computation. If you remember back when we were working with MLPs, we flattened the image data like a vector. And here we are somehow doing that again. So if we want to compare that with what we did in text. So in NLP, we extract these word tokens, and we discussed that we have different ways of doing this tokenization. Here in computer vision and image data, we are working with patches within these images. In the NLP, we work with the encoder transformer to find the representation of the sentence. We do the same here too. Output, same. We have this token embeddings that is the output of the encoder transformer. We do the same and we encode this patch embeddings. So in the seek-to-seek architecture, we did translation and we really decode to another sequence. But we could just use the encoder part and do text classification. Here we do the same and we use the encoder to find this representation of the image and send it to a classifier head. So this is a sketch of what I just described. So instead of using the complete transformer encoder decoder, we only want to use the encoder. We get this input tokens, and we add another token that attends to all of these input tokens in the same self-attention block. And since CLS token or classification token see all of these other tokens, we can just use it as a output of the encoder, which will be a transformed token, and send it to the classification head and get the logits. Okay, so basically we are not doing any translation. We just understand the input token and do classification, just like what we did for image classification using our CNNs. So you will see this classification token later in other architectures when we work with texts. But you could think of, well, what if we don't have this and we just take in the input token and transform them and get the output tokens and then just average them using some learnable fit for a neural network to get the average representation and then send it to the classification? Well, the idea is we are somehow doing that in the transformer encoder. So we send the CLS embedding here, and we are doing it in a more flexible way that the simple averaging cannot do it. In a more flexible way through this self-attention mechanism that the separated averaging is unable to do. So that's really the idea of this CLS token. And you can also think of, we basically don't touch the transformer encoder and the classification head by just adding a token here. So it's also more easy on the pipelines that we already have. So here is the vision transformer pipeline. We divide the image into this similar size patches, and then we flatten them as vectors and we feed them to the patch embedding layer. So note that we have a positional embedding here. And again, the reason is self-attention doesn't really care about the order. And we know that a proximity of this pixel values really has meaning. That was one of the rules or induction biases that we infused to our CNNs. Now, how to do this positional embedding? We have different options, and we will talk about some of them. But the main point here is we basically add this positional embedding like a bias to our tokens and find this more oriented tokens and send it to the self-attention mechanism, which is similar to what we had in the transformer encoder. And at the end, we get this transformed representation for each one of these tokens. And we only use the CLS updated representation for our classification. So some more details on how to do this patching. For an image of heights and widths H and W, we divide it into P by P non-overlapping patches, which means we will have T patches. For example, for an image of 224 by 224 3-channel RGB, a 16 by 16 patch will result into 196 patches. Note that we have 3 channels, so each patch will result in a vector of 768 values. This is similar to convolution, where we had the kernel size and stride similar to this patch size. So this means basically the kernel is the patch and they are non-overlapping. On the positional embedding, like I said, self-attention is permutation invariant. So we have to infuse some knowledge of the spatial location of these patches. And this is how we do it. So after we getting these values, let's call them X for each patch, which is projected into this vector embeddings. And then we add the positional embedding into each one of these embedded patches, including the CLS. So you may think of why we are learning the position again, because like I said, this is a learnable like lookup table. And why we are wasting learning on something that is already there. We can have indices for each patch. Firstly, the amount of learning or the number of parameters that we are spending on this positional learnable position embedding is peanut really compared to the entire parameter. But also, it's not really restricted to just looking at the surrounding patches anymore. And it can learn richer geometry than the Cartesian geometry. So basically, it's more flexible. That's what I'm trying to say. Moreover, the authors of ViT paper, they showed that replacing the learnable embedding with the indices of the patches really doesn't give us any gains. and we are losing flexibility. Another important distinction from the original transformer is where to place the layer norm. And if you remember, the original transformer has the norm after the residual. Here in the ViT and other modern architectures, we have the layer norm before the layer. So we discussed that before, that such a pre-norm setup that does the normalization before the addition of the residual path makes it easier, really, for the gradient flow. And also during the training, we really don't need to be very careful at the beginning because of those issues. So we can push the gas pedal on the training sooner. Okay, so, well, we had lengthy discussion on why CNN uh, brings these inductive biases and all of those benefits of doing that. For example, the translation invariance looks for patterns, no matter where is that pattern, right? So the same weights can be shared regardless of where we are looking at. And for a local feature, only nearby pixel really matter. If there's an edge, we really don't need to look elsewhere. There is an edge, right? So that means that we can use finite kernel size, and then the hierarchical receptive field based on this small kernel size will give us the bird eye at the end. This leads to strong prior. So this strong prior helps us to train this CNN architectures using medium-sized data sets while generalizable on unseen images. But the question here is, does that inductive bias limits the capacity of CNNs or basically creates a ceiling on what CNNs can do? I mean, yes, they are very regularized because of that and very efficient in terms of the number of parameters. But does that mean that they are less expressive? And we may miss something in terms of the amount of learning. So that's the hope that we can fill in with transformers, because transformers are really they don't have any of those biases. There's no locality bias because self-attentions look at all pairs. We are not enforcing translation invariance, and we let the position embedding to be learned. So that means that the content of the image is not really a hierarchical reasoning of these spatial proximities. For example, putting edges together. It's something more than that. So for example, an edge can be a different edge when we are looking at somewhere else in the image, which is not next to that edge. So we can interpret that edge differently because of that. This lack of geometric spatial proximity that we enforce in CNN, but not here in the transformers, allow the transformers to learn something else that we could not learn in CNNs. Okay, so to summarize, we are doing a trade-off. CNNs, we have strong handcrafted biases, which led to sample efficiency, but there might be a plateau in the performance. In the vision transformers, we have minimal biases, which requires much more training, so we need more data, but they are transformers, and we know that transformers are scalable. And now, when we give enough data to these transformers, this more capacity can lead for better learning. Okay, so let's see the empirical evidence for this hypothesis. So for that, we go to the original paper for visual transformer. So here, x-axis is basically the number of JFT pre-training samples, and JFT dataset from Google. So we look at the model pre-trained by this many number of samples. The y-axis is the accuracy of a linear probe trained with 5 labeled examples per class on top of this frozen pre-trained model. We see that with small pre-training sets, resonance are still better, but they plateau while we give them more data, more images. For example, from the 30 million to 100 million, then we don't see any improvement for the resonance. However, when we provide large training sets, the visual transformers overtake CNNs and they continue improving. So the plateau may never happen. And that's the idea that we will look at later. Here, just to read the image, the rest of these curves, we only focus on this light blue and the black ones. But the rest, here L stands for large, B for base. This lowercase b is a base model with half the hidden dimensions of the original one. The numbers 16 and 32 is basically the patch size. And we see the large visual transformer with a patch size of 16 is surpassing the CNN and continue improving. So this gives us a recipe. The modern machine learning paradigm is pre-train on massive data sets, billions of examples, and then fine-tune on downstream tasks with much less data. So the pre-training often is done with much larger resources and compute, and the fine-tune can be done in commodity computers. So in such regime, transformers really excels. We even have a scale that we know how much it improves, so we can even invest on it. We know that there is not a plateau, and with the amount of resource that we are willing to invest, we will get this much improvement. And this result is really across all modalities, not just images or text. So next, we will talk about the scaling laws and then much larger pre-trained models in natural language. And then we discuss this idea of having these pre-trained models and use them as foundation models that can be fine-tuned for different tasks. But before doing that, let's go back to Visual Transformer and discuss the major problems that it had in this small, medium dataset regime. Like I said, we're dealing with this lack of inductive bias, which means that they can overfit very easily in such regimes, and they really need more data to be able to shine. And the other problem is we're dealing with a quadratic cost complexity with this number of patches. And we are not looking at different scales, like, for example, smaller to larger scale in a pyramid-like scheme like CNNs. We basically look at every pair of patches at once. So the idea is, well, maybe we can use some of the lessons that we learned from the CNN trainings. And at the same time, we can use this transformer scalability. In other words, can we inject some of these CNN priors in different points of this vision transformers? Well, I try to categorize them in three different categories. The first one is basically we look at this front ending the feed to the transformers, which basically we give we do some pre-processing of the data using CNN stems and then feed that features learned by CNN to the transformer. The other idea is to use this hierarchical way of learning in CNN, but use that within transformer architectures. And then the other idea is to bring a CNN that can teach our transformer. So at some point, the student can be better than the teacher. And that's the distillation idea. So this is the data efficient transformers. So really, there was another idea here that basically we can think of expanding or inflating the data by different augmentations. And this way, we basically somehow artificially increase the number of data points and let the transformer believe that there are more data. So this way, transformers start improving. So it's a combination of these two, which somehow implicitly bring the CNN into the equation. The other two, we really bring the CNN idea explicitly into the equation. For example, in this hybrid ViT, we have a CNN at the front of the transformer. But in the third one, we let a CNN to guide our transformer. So we will focus on the third one because of its flexibility. Basically, we still have a transformer, and we are not really limiting its architecture. We just train it using a CNN. So we are not losing any of those flexibility and scalability properties. And we keep the transformer pure. So the idea is coming from this paper by Tuvron et al. From Sorbonne. And the goal was to make ViT competitive on a small scale data set, an ImageNet more specifically. Like I said, the insight is let's use a CNN. And back then they used this uh, CNN that was the state of the art as a teacher that transfer its knowledge through this distillation process during training. Like I said, they also consider augmentation, regularization, and then some other techniques along the way. But really the main idea here that I want to talk about is this distillation idea, because somehow we will talk about variants of this even in the language models. So here they add a distillation token, just like the classification token, that learns from the CNN teachers' predictions and softly imports this prior the teacher has into the training. So here is a schematic from the paper. You see the class token and the distillation token. And here we have two laws. One loss is basically looking at the transformed class token and do the classification based on the real data. And the other loss is to predict the prediction of the teacher. And once we deploy the model, we only look at the prediction, the real prediction of the model. But this will guide this other transform token. So you may think, oh, well, how can the network can be better than the teacher? Well, it's just like how you guys will be better than me. You will see other things and you will decide for yourself, right? This is no enforcement. This is just a loss and a trade-off that the model will do. And eventually it is exposed to the real data and real labels and will learn what it can learn from the both classes. So this is maybe a zoom in into the training where we get the patches and then we do the embedding along with the CLS and these tokens, and then the same transform encoder. We're not touching this, and we only use two of the transform tokens out of the transformer, and one will be fed to the distillation head and one to the classification head. The distillation head gets the labels from a frozen CNN teacher. The classification head gets the label from the data. Okay, so let's zoom into these last terms and how they are handled in this setup, as this is a good exposure to knowledge distillation, a technique that basically a smaller student network learns to mimic a larger or better teacher model. Here CNN, and the student is the transformer. Okay, so to do that, let's look at the paper. So here we only look at the class token. There's not yet a distillation token. And if we want to do the distillation only with the class token, first we compare the prediction of the class token, which is the softmax, with the true ground truth label using a cross entropy loss. And also we add a KL divergence that basically enforce the network to learn the same distribution for the logits as the teacher. Okay, so this is kind of soft label distillation, meaning that we learn the distribution, the prediction. So we learn the distribution of the prediction of the teacher here. So this is a soft distillation. But the authors discuss this hard label distillation, meaning that we want to look at the prediction of the teacher as if that's a label. And in that case, we go to the hard distillation, which we want to not only predict the ground truth, we also want to predict the best guess of the teacher, not the distribution of the guesses. And here is where the authors are discussing this new token, the distillation token, to basically separate the two losses using two heads. So using the distillation token here from the distillation head and using the class token here in the class head. And they showed that this way, the network actually learns more than no distillation. And also they showed that a CNN teacher works better than a ViT teacher. Although the ViT teacher does a better job by itself, but it's not a better teacher for our architecture. And the reason is basically CNN teacher brings something that is different. It's a different inductive bias that the transformer doesn't have. So the student, while remaining flexible, also learns what the teacher knows. So that's somehow uh, reinforcing the assumption that diversity helps, as that leads to a richer learning signal. So the teacher model is only active during the training, and the model learns to use both tokens effectively. And during the inference, of course, we don't need the teacher anymore. And we can also skip the distillation head, but the authors suggest to keep it and make an average of the two to basically do this kind of consensus to achieve a better performance. So this is the first figure of the same paper where they showed the distilled version of the network works better than the comparable neural network with similar resources. So here that is efficient net, and we also already discussed that in the previous lectures. And we see that with the same amount of latency or compute during the inference, the distilled model works the best. Note that this is the same model without distillation. So we will see knowledge distillation later, but note that here we basically transfer these biases across these architectures. And instead of a mere compression, we instead bring an efficient learning, that the smaller model is not really copying the teacher, but it's learning from the teacher and eventually becomes better. So the teacher's signal is not really replacing the ground truth. It is supplementing it.